Good afternoon, everyone. This is the second tutorial in the emerging topic section on probabilistic programming. So in the next 2 hours, Frank Wood will introduce us to probabilistic programming, both as a general concept and in terms of how current systems work. Probabilistic programming is a very truly new emerging topic, and he'll shed a light for us on the historical academic context of it, as well as expose some challenges that are very unique to probabilistic programming. Frank will also introduce us to Anglican, so there's going to be some demos. Anglican is a software system that allows everyone to write probabilistic programs. So after you leave in 2 hours, you probably write your first probabilistic program yourself. I personally think that probabilistic programming is one of the most elegant ways to define large and complex probabilistic models and use the compiler and interpreter technology to automatically perform model-based inference. I myself had made first experiences and contact with that new form of programming back in 2009, and I actually believe that it do have the potential to increase the number of people who can build and understand their own models by several orders of magnitudes. Before I hand over to Frank, I'd like to tell you a bit more about him. So Frank's currently an associate professor in the Department of Engineering Science at University of Oxford. That's a position he took in 2013 when he moved from an assistant professor position at the statistics group in Columbia University. Before that, Frank was a postdoctoral fellow of the Gatsby unit, and where he graduated under supervision of UIT, and he received this PhD from Brown University in computer science under supervision of Michael Black and Tom Griffith. One of the most interesting things about Frank is that he's not only a stellar academic in a very interesting new field, but he's also a very successful entrepreneur. So prior to starting his academic career, about 7 years ago, he was actually running and selling a content-based image retrieval company called Twofish to Time Warner, and he was serving as the CEO of Interfolio. So he started his career working at the Cornell Theory Center and subsequently at the Lawrence Berkeley National Laboratory. When Frank's not working on probabilistic programming these days, he plays the ukulele and the trumpet. I wonder if we get some of that to see today. One of the things with Frank is he's really the NIPS conference is really quite an unfortunate conference for him. He's drawing a bit of bad luck in recent years. So last year he knocked himself out for almost all of the conference by food poisoning. And this year, when he traveled, he perforated his eardrum. So if you'd like to understand him when you walk up to the microphones later, you really need to speak up loud. So without further ado, let's welcome Frank.
Thank you, Ralph. Can everybody hear me okay? Yeah. I apologize in advance. Ralph is absolutely correct. NIPS is notoriously bad for me health-wise. I think out of the 10 or 15 years I've been coming to NIPS, I've lost my voice twice and been unable to talk to anybody at the conference, food poisoning once, and this time I have slap cheek, which I got from my kid at nursery, and I've never had it because I'm American, and it's just absolutely terrible, and I've lost all of the hearing in my left ear, and I've got about 25% hearing in this ear, and everything I'm going to say I hear reverberating in my head, so this is going to be terrible for me, probably for you too. And I would hope that beyond all that, if I can get through this, first of all, I apologize for coughing and making all sorts of terrible noises. I have my tissues here. I hope that my health issues don't get in the way of me expressing my excitement about probabilistic programming and how cool I think it is and how important I think it will be for the future and evolution of machine learning. So, without further ado, my objectives for today are to get you to know what probabilistic programming is and how it's different to normal programming. Seems like a reasonable objective. To roughly understand how to write a probabilistic program and have the resources to get started doing so if you'd like to try to do so. I'd like to give you a sense of where the field is at and where it's going. Probabilistic programming has been around for longer than a lot of us recognized. And because this is a tutorial, not only will I talk to you about how to program in a probabilistic programming language, but because many of you are machine learning experts and inference experts and people that we'd like to have interact with us on the back end of probabilistic programming systems, I'll try to get you to understand at least one way to roll your own state-of-the-art universal probabilistic programming system. Okay, so what is probabilistic programming? I would ordinarily, so how many of you come in with a preconceived notion of what probabilistic programming is? Okay, that's the problem with NIPS. You all are experts in everything already. So I'll just tell you what I think probabilistic programming is then. So the field of probabilistic programming, in my opinion, is centered in the mix of machine learning, statistics, and the programming languages communities. One way to say what probabilistic programming is about is using programming languages techniques to abstract inference algorithms from stats and machine learning such that they apply automatically and correctly to the broadest possible set of model-based reasoning applications. Okay? So we're going to take algorithms and applications from machine learning. We're going to use some of the theory from statistics and tools like compilers and source code transformation and so on and so forth from programming languages to build systems that help us do model-based reasoning automatically and in models that would be otherwise very difficult to imagine doing such reasoning in. In terms of intuition, building intuition about what probabilistic programming is about, this is my way of sort of explaining it to people who don't have a preconceived notion about what probabilistic programming is about. I say in computer science, we're given a program, or we write a program, and it has some sort of parameters. And then we compile that program and we run it, and running that program produces some output. Okay? That's the standard computer science story. The statistics story is pretty different. In statistics, in computer science, we don't have the output, we produce the output. In statistics, we actually have the output most of the time. So in statistics, we have the output, some observations, some data, so on and so forth. And we make up some model. Let's go with a generative model because we're doing generative modeling and model-based reasoning in this probabilistic programming context. So we make up some generative model for the data, and it has some variable, latent variables X that are explanatory with respect to the data in some way. So, you know, again, in computer science, we're given the program and the parameters, and we run it to get the output. In statistics, we're given the data and the generative model, and we have to do something to figure out how to turn that process around and learn something about the variables X that could have given rise to the observations Y. So, probabilistic programming, in my view, is the computer science way of doing statistics. It's sort of the computer science formalization of the statistics process, where in place of the generative model, we now have a program. So we're just going to write our generative models as programs. We're going to, that's basically the same thing. The output of the program is going to be given to us now. And those are going to be our observations. So we have a generative model, we have whatever that's our program, we run it, it generates observations, but we're given the observations. And the task then is to figure out what parameters or distribution of our parameters or whatever could have given rise to the observed output. And we're going to use the tools of statistics and machine learning to do this, and we're going to run inference over this and invert this process just as we do in statistics, where now the representation of the model is some sort of programming language construct, and the inference task is rather general because of the expressivity of the representation. How would you identify a probabilistic program if you were to see one on the street? Well, I think Andy Gordon and colleagues defined it relatively nicely. Probabilistic programs are usual functional imperative programs with two added constructs. One, and this is very standard in programming languages, randin, gamrand, whatever. The language has to be endowed with the ability to draw values at random from distributions. So this is completely standard. But the novel feature is that a probabilistic program has some syntactic representation of constraints. It has the ability and some semantic capacity to constrain or condition the values of variables in a program via observations. Okay? So probabilistic programming languages will have constructs, syntactic constructs for both of these, the ability to, these random number generators, but also the ability to condition the program executions based on observations. And that's pretty different, and actually, despite the fact that many, many hands went up, I suspect that most of you will, it'll take a little while for that to sort of sink in. What are the goals of probabilistic programming? Well, one goal is to make individual programmers much more productive by radically decreasing the coding effort involved in making new models. So we all are very happy with our small set of models that work incredibly well, and Inference works beautifully in those models. But it's always complicated to cram your analysis or your modeling problem or what you want to do onto one of those small formulas. And so you're always wanting to build new models, and building new models is complicated and painful. You know, you have to read a paper, and then you have to write the generative model, and you have to write the inference procedure to go along with it, and it's buggy and so on and so forth. One way to, what we'd like to do in probabilistic programming is make that a lot easier, that model innovation step incredibly easier. So this plot shows actual reduction in code complexity in terms of number of lines of code, keeping it pretty honest, actually. And these are personal experiences from my own lab. There's lots of other labs that could report the same kinds of things. So on the vertical axis, we have lines of Anglican code, which is one of the languages I've been involved in developing. Again, this plot would hold for almost any other probabilistic programming language. And on the bottom here, we have lines of MATLAB and Java code. And each of the blue dots here is an example model, some of which you'll be familiar with, some of which you'll be less familiar with. On the bottom left, we have collapsed latent Dirichlet allocation, or a Dirichlet process conjugate mixture model. And then falling further away, we have in the middle an automata induction model called the probabilistic deterministic infinite automata. And on top, we have the dependent Dirichlet process mixture of objects model for object tracking, and the hierarchical bitmap neural process over in the bottom right-hand corner. And the two lines are actual regression lines, map regression lines fit by an Anglican query that tries to decide whether or not there's a logarithmic or linear gain in coding complexity. I don't believe either of the lines. That's not really the point. The point is that there's actually a real reduction in the number of lines of code, and it's about 10 times. Okay, so that's a real savings. And where does that come from? It comes from two things. One, amortizing inference. So obviously, in all of these, we're not going to have to actually write inference code to go along with the model. We just write the generative model, and the system provides inference for us. But also, the expressivity of the language makes it easier to write complex models, and that's a critical feature. Another goal, and which is complementary to the last goal, is to remove the burden of having to develop hand code inference. This is complicated, buggy, painful, something that you have to do for every new model that you want to write down. And this we do by specifying an abstraction layer, an abstraction boundary, a language representation layer in which models can be expressed and inference engines can be plugged in, such that if you write your model in that representation language, you get inference for free. You don't have to write inference code to go along with it. And there's, very importantly, a community development thing at play here as well, which is that when you have abstraction boundaries in place, communities can develop the work above exclusively, working on models and applications and so on and so forth, and below, inference, those of us who work on inference almost exclusively, can work below this area, this boundary, and we can feed off of one another in the field of machine learning and probabilistic programming can advance much more rapidly. In my way of thinking, the NIPS community has a good representation of both, but probably most of the people who would work on what I would call compiler optimizations or inference engines are at NIPS. So this is, part of the talk is targeted at you saying, look, if you want to write inference, write it in one of these systems where you can test it on all sorts of models that have already been written in the language. And for practitioners who are struggling to make models for whatever domain they're working in, why not try out a probabilistic programming language? The worst that you're going to get is generic inference that's slow. The best that you're going to get is an answer. You can be done. So that's pretty attractive. And the last goal for probabilistic programming, and the one that I'm frankly most excited about, is is the development of sufficiently flexible model specification languages so that you can actually contemplate writing down the kinds of models that you really always wished you could write down, but were maybe intimidated by the prospect of having to notate them mathematically, so you didn't. My own personal experience with this is that we can all dream up crazy awesome models over source code generation, and then running the source code to produce output, or scene descriptions, or simulators that we can write to simulate our data, but we don't know how to invert them, so on and so forth. Let's liberate ourselves and at least make it possible to write these kinds of models down. And finally, the final goal for probabilistic programming is that when you've got a hammer, everything starts looking like a nail, right? And I think for those of us who are working in probabilistic programming, that's one of our goals, is to make probabilistic programming like that. And we will have succeeded if the first thing you do when you're faced with a novel modeling or model implementation task is to open up an Anglican Gorilla REPL or a Web People session or a Venture Interactive shell instead of an IPython notebook or MATLAB. And this is very telling. In as much as I'm able to code and do my own modeling and these sorts of things myself, I have gray hair, I'm a professor, I don't get to do as many of these things as I would like to. When I do, I now default to a probabilistic programming system. I don't open MATLAB, I don't open IPython notebook, I just use one of our systems. And that says something about where we are now. You may not be aware that we're at that point. So where does the field come from? Where it's going, so on and so forth. The field of probabilistic programming has actually been around for a really long time, although it hasn't necessarily been identified as a field as such. And this figure shows a reasonably comprehensive set of languages listed on the date they first appeared in the literature. And I apologize to anyone who has a language that they think should be up there. I did the best I could. The key points here are that researchers in multiple fields, programming languages on the left, artificial intelligence, machine learning, statistics, have all independently and repeatedly recognized the importance of using programming languages formalisms to abstract problem and model specification away from the specific algorithm used to compute an answer. And of course, it would take many hours, many more than I have today, to go through all these languages and what motivated their design. And frankly, a historian of science would be much more well suited to explaining their relationships and analyzing their relationships, and probably would be less likely to offend if getting something wrong. So instead, I'll point out a couple of notable success stories, and then proceed to tell you why I'm not going to talk about them. How many of you have used bugs? Okay, this is not a statistics audience. Okay, how many of you use Stan? Okay, awesome. Factory? Info.net? Okay? Okay. So these aren't raging success stories, any of them. No, not any, one got more than 50 people putting their hands up or something like that. But I would go out on a limb and say that if you're using graphical models, then you should stop custom coding and use bugs or Stan instead, if you can. And if you're working with factor graphs, you should stop custom coding and you should invest the time to learn Infer.net or Factory. And just to throw it out there, Figaro is another up-and-coming system and language that should probably go up on the factor graph side of this slide, but it doesn't have a splashy logo, so I didn't put it up there. So the question is, why are these success stories? There's some network effect, that's for sure, but they all nicely address well-understood abstraction boundaries where inference works and people have lots of experience writing models. So let's look at them in just a little bit more detail. So Bugs is one of the earliest probabilistic programming languages. To be fair, it's actually not really a full-fledged language. It's an imperative model specification language that allows finite graphical models to be expressed. On the top left, there's a simple model expressed in the Bugs modeling language. If you were to write down the corresponding mathematical denotation of this model, it would be what we call a Gaussian unknown mean model, where what we say is x is some random variable which is normally distributed with mean A and precision B. I forget its precision or variance, doesn't really matter, standard deviation. And then there's some number n of observations y which are normally distributed given mean x and some other parameter c. Great. Outside of this, there's a data frame which binds the values of A, B, C, and Y. And what the inference engine does is, because there are these language restrictions, so I can't go through the entire grammar for Bugs and point out the language restrictions, but you'll just have to take it on faith that you can only write bounded loops. N can't be a random variable, and you can't have an infinite loop or an infinite recursion here. There's no branching in the language, which means that you can take that model and you can unfold it directly into a data structure, into a finite graphical model, and then do pattern matching on the Markov blankets of the nodes in that model to Gibbs operators, and then run inference on the resulting graph. You just run a Gibbs sampler. Great. So we have this lovely setup where we have a language which allows us to express models. It's restricted appropriately such that it corresponds exactly to a particular model class, and that model class happens to have inference algorithms that work for that model class. Great, done. If you're working on small graphical models, if this were a stats audience, and when I asked who used Bugs, 75% of the people would have put their hands up. Okay. Following on from that, Stan, of which many more of you have raised your hand when I asked whether or not you used it, is another success story from the probabilistic programming community, and it's a real groundbreaker for the stats community. It's billed as a replacement for Bugs with better inference, but it's actually much more interesting and advanced than that. So if you note, there's a similar kind of modeling language, although here the modeling language is much more expressive. The model block here is like the Bugs model block. There's a parameters block above it, and there's a data block that's outside of this as well. Here, instead of the Gaussian unknown mean model, this is a linear dynamical system where we have some the first x is normally distributed, and then some number of x's are normally distributed with a linear scaling given the previous x's, and then we have some observations drawn from that latent backbone of x's. The modeling language here is much more expressive than what you see here. It's actually not an imperative model specification language, but it's actually a procedural description of how to run this model. It still has restrictions, bounded loops, and a big one for Stan, no discrete random variables. But with those two things, the models that can be induced by running this program correspond to finite dimensional differentiable distributions, or at least differentiable with respect to the parameters in the block, which means that you can use much more advanced inference techniques, including advanced variants of Hamiltonian Monte Carlo, where we see our first sort of programming languages trick show up, where you can use reverse mode automatic differentiation to get the gradient, shown in the upper right-hand corner, necessary for Hamiltonian Monte Carlo, at the same time as evaluating that program in a forward pass. The reverse mode gives you the gradient of that parameter with respect to its parameters. So you can use that within a Hamiltonian Monte Carlo loop. Stan also has a black box variational inference, so on and so forth. Great. So here we have, again, a lovely modeling language. It has some restrictions. The restrictions make it so that inference of a particular flavor can be run. Lastly, we have factory infer.net, Figaro maybe. The code snippets for these languages are much too long to fit on the slide, but both are a sophisticated and scalable model specification language that allow finite compositions of factors and provide generic inference algorithms for performing inference on the resulting graph. In particular, message passing is shared by the two of them. Again, same story. Model specification language allows you to build finite compositions of factors. You can run lovely inference algorithms on the resulting graphs. Great. I bring these to the fore just to drive home the point that probabilistic programming tools and techniques are actually creeping into the realm of scalability already. So today I learned for the youngsters out there is that when you get matched on Xbox Live against random players based on your skill inferred by past performance, it's a huge true skill model, so the model down there in the bottom left, solved by infer.net that infers yours and everybody else's skills so that you don't get mercilessly and immediately walloped by superior players. And I would say, if, hats off to them, infer.net is in particular probably the most scalable of any of the probabilistic programming systems out there, and that it is actually already deployed at an industrial scale. But I said I was going to point these out as success stories and then tell you why I'm not going to talk about them. Those languages are all very well designed for their targeted model classes and corresponding inference algorithms. But the programming language that there is very restrictive in all of those cases, and yet, and that's really why that's one of the reasons why people like me are continuing to work on new programming languages. So what I really want is to be able to write down my model in any way that I want. I want a completely unrestricted model specification language that allows open universe models or infinite dimensional parameter spaces, mixed variable types, unfettered access to existing libraries so that I can build simulators that use renderers or physics engines or whatever else. And I like it to be easily extensible so that I don't have to go write special custom factor code if I decide to put in a new operator, or if I decide to put in a new distribution, I don't have to go in and change the Gibbs sampling code. So great. So we'd like to do this. This is going to come at a cost, and that is that inference is going to be harder, definitely, because we're not going to be able to use special purpose inference algorithms that correspond to restricted modeling languages. And by giving ourselves this freedom, there are going to be lots more ways for us to shoot ourselves in the foot. So if we're looking for languages that satisfy these desiderata, that simplifies the picture that I put up here before quite a lot, the languages in the, I guess, I don't know what colors those are over there, in the blue, only support bounded recursion, so fixed finite dimensional parameter spaces, which means that specialized inference algorithms can be employed, but richly expressive models cannot be expressed. and the languages in the red only support discrete random variables, which again limits their appeal when you're looking for an unfettered language in which to write. And this leaves the unshaded region up above, populated largely by machine learning inference, which are not fettered in this way. They allow unbounded recursion, they allow mixed variable types, so on and so forth. They're expressive in ways that the others are not, and for this reason are the systems that I'm going to focus on and tell you about. And if I allow myself a little bit of grandeur, I think they're the languages that are going to pave the path towards actually achieving AI. Because we're going to need to build tools like the neural net community has built for dealing with huge neural nets and dealing with derivatives and taking them for you automatically and so on and so forth. We need to do the same thing for inference and reasoning, and these languages are the kinds of languages that allow us to write down any sort of model and express inference over the same. So these languages exist. The question is, what are people doing with them? If you set yourself free, what kind of models can you imagine? What are you going to do? Are you going to go crazy? Let's take a look at a couple of examples, starting with this. So a couple of years ago, Vikash Manzika and colleagues, got a paper into NIPS called Approximate Bayesian Image Interpretation Using Generative Probabilistic Graphics Programs, which was a real eye-opener for a lot of us. And in it, they posed vision for the first time, sort of, not for the first time, that's been posed this way before, but they made it practical to consider vision as inverse graphics and showed that you could actually do it in an existing probabilistic programming system. And one of the examples that they showed in the paper is fairly indicative of the kind of power that we would expect from these unfettered probabilistic programming languages. For instance, they showed how to use a probabilistic programming system to solve CAPTCHA. So here, the latent variable is a scene description. So you can imagine, this is one of these modeling situations where having the power of a language and libraries and so on and so forth is really going to be helpful. You can imagine writing a simulator for CAPTCHA pretty easily, right? Pick some unknown number of letters, move them around a little bit, blat them to the screen. There's your generative model. Okay? Writing that as a factor graph or a graphical model or something like that is going to be very, very difficult. But if you have a piece of source code and a simulation environment, it's really easy to write this down. Right? What's remarkable is that you can be given an image in Venture, and that the system, given that generative model, which is described as just a procedure, right, with picking a random number of things, blatting them down, running them through a simulator, so on and so forth, the system is capable of inverting that and recovering, given y, the output of the program, the random variables that gave rise to it, that being the settings of the simulator. They also had a road finding application in that paper, which was also extremely illuminating. But they were simple in some sense. But they came back with a roar this year with a paper called Picture, and introduced a new programming language called Picture, a probabilistic programming language for scene perception at CVPR this year, where they took it a step further and actually started doing inference over really fairly complicated scenes, graphic scenes, where, say for instance here, the latent variables are some sort of mesh and its deformation, the pose and lighting of a face, and the output is that scene description rendered down to a face. Now give me an observed image of a face and use the probabilistic programming system to invert that transformation and recover the latent variables that describe that. So X and Y are shown there under the scene description, and then once you have the representation of the face, in terms of the mesh deformation, lighting, coloring, so on and so forth, then you can play around with it and relight it and infer different poses and so on and so forth, which is cool. And they did this with pose estimation and physical objects as well. It's pretty nice. But again, powerful examples of what you can do when you have the power of a general purpose language and a simulator on your side in terms of writing models. Other examples of things that are difficult to think about modeling outside of the probabilistic programming framework come from Andreas Stuhlmuller and Noah Goodman, among other people. And one of the things that they're interested in doing is reasoning about reasoning. So a typical example of this is the Schelling coordination game, where you have two people that would like to meet up, but their phones are dead. They can't communicate in any other way. Say, for instance, here, Andreas and Noah would like to meet somewhere. They can't talk. And what they want to do is simulate, recursively, mutually simulate each other to reach some sort of conclusion about where they're going to go. And so we model Andreas as a program which knows that he wants to go to the pub, but then calls some other procedure which says, where will Noah go? Which simulates Noah. And when you simulate Noah, Noah knows that Andreas wants to go to the pub, and Noah's a nice guy, so he'll go wherever Andreas goes, but he could go somewhere else, and so on and so forth. And you iterate this process to some depth, and this reasoning process works out, and there's stable points and so on and so forth. But the point is that if you want to write down something like this, that's some sort of cognitive process and rooted in some sort of behavior where you're doing mutually recursive simulation of actors in an environment, it's very difficult to think about how to write this down in any other way than in some sort of procedural representation or probabilistic programming language. Another thing that I've been involved in, which is a little bit of a mind warper, is exactly what I said before, thinking about doing program induction. This is work that I did with Yura Perov. We talked about it last year at the ABC workshop, where sorry, the videos are over. I'll maybe replay them. On the upper left-hand corner here, we have a prior over programs. Okay, so how do you write a program? What's a PCFG, and after a PCFG, if you want context dependence, then you have to have something else, so on and so forth. We're going to write S expressions. We're going to write programs like this. And the goal that we had in mind was to be able to write something like Marsaglia or Gamma or something like that, a program that actually itself knows how to sample from some distribution. So you give us the distribution here on the right, Y, in blue, so I'll go back here. We write a program which generates source code, yeah? We run the program, that's the stuff there in green. Running the program, we write a program which itself generates samples, right? So that we're writing a program which is a sampler. Our observation, our global observation, is the program output. We'd like to test whether or not the output from the program, this Y tilde up here in the upper right-hand corner, matches the distribution of interest. And if so, what we'll report is the program that did so. So here we're just sampling away, generating programs, so on and so forth. And you see on the right-hand side here that we're exploring the space of programs and eventually find a program that does a fairly decent job of generating samples that correspond to the distribution of interest. Okay, so we've learned how to program. Okay, pretty cool. And the last example for now is, and I think maybe the most immediately illustrative example of what probabilistic programming is about, because it's so visual and compelling, is this notion of constrained stochastic simulation. Again, Ritchie, Goodman, Hanrahan, and colleagues have built probabilistic programming systems, so on and so forth, and some beautiful example applications of things that would be difficult to model or to reason about outside of this kind of framework, where, for instance, on the left-hand side, they searched over the space of stable structures. So they built a program that built structures and then ran them through a physics simulator to see whether or not they fell over, right? So how do we build bridges? Let's do mechanism design, okay? We're gonna write a program that builds something. We pick some number of blocks, we stick them on top of one another, and then we run it through a physics simulator and observe whether or not it falls over. And we condition our program on those that don't fall over, and we say, give me the stable structures. That's pretty cool, okay? That's a different way to do design, and I think that has potentially profound implications for engineering. And on the right-hand side, they show something really lovely, and I use this example quite a lot. I think it's a beautiful example of what probabilistic programming is all about. So if you're Pixar, and you want to put a forest in a movie, and that forest has 1,000 trees or something like that, you don't go off and hire 1,000 graphics experts to make individual trees. What you do is you hire one very good programmer and tell that person to write a stochastic tree simulator, right? And then you run that program 1,000 times, you have 1,000 trees, there's your forest, okay? So that's procedural graphics in a nutshell. But what if John Lasseter comes in and says, hey, I want that tree not to hit those 3 gray bars, or I want that tree to go around that logo, right? So this is exactly what probabilistic programming is about, and visualized very directly. So the evolution of the program is actually the growing of the tree, and the constraint here is don't hit the thing, right? So now we have, again, a framework where how do you write down a model for a tree like this? There are material diffusion trees and so on and so forth, but writing down a model of a physical tree, really the easiest and the simplest way is to just write it down as a recursive simulation, a recursive branching procedure. And then if you have directorial constraints or observations of don't hit this, you can impose them and then ask a probabilistic programming system to invert that and say, give me the trees that didn't hit this stuff. Okay? So this is a whole new way of doing procedural graphics, and I think it's going to revolutionize graphics, film production, so on and so forth. Great. Okay. Thoroughly motivated. Yeah? Lots. Now I can't turn my head away while I'm coughing. That's the problem. But okay, sorry if I've been going in and out. I apologize. Okay. Great. So we've got a bunch of models, and we've got a bunch of things that we would like to do, and hopefully it's clear that what we need when we're contemplating these kinds of applications is a fully unfettered modeling language. So what do these look like? And I'm going to call that kind of modeling language a universal probabilistic programming modeling language, just to clarify. I don't mean anything by it other than it's not restrictive in the ways that the other languages we talked about are. And really, I don't mean to play favorites here at all. There are lots of interesting languages out there, Anglican, Church, Venture, Web People, so on and so forth. And they all have this unfettered nature. I happen to be more familiar with Anglican, so I'm going to show you Anglican syntax and so on and so forth. But sort of the way one writes programs and how one introduces constraints and so on and so forth is shared by all of the modeling languages of these systems. So if you grok what I'm getting at in the next 10 or 15 slides, then you should be able to go off and write your own programs in any of these languages without too much trouble. Okay. Ordinarily, just so you know, at this point I would say, hey, are there questions, so on and so forth. But with an audience this large, I just have to talk at you, and it's very, very uncomfortable. But do feel free to interrupt me if there's a burning question, or in particular if I get something wrong. So, syntax. So Anglican is a lot like Cloture. How many of you have programmed in Cloture? Oh, as many as Stan. That's good. Okay. So Anglican is a lot like Cloture, which is a lot like Church, which is a lot like Lisp syntactically. And I'm sorry for doing this, but you're going to have to look at some parentheses. I'm going to show you some source code, so I'm going to give you the bare minimum that you need in order to read along with me. It's not that painful. Once you get used to it, it's actually really beautiful. So first of all, Anglican uses prefix versus infix notation. So if you want to add two numbers, plus is a function. The first thing inside of a parentheses is the function that gets called. Plus 1, 1, you can probably guess what that does. If you want to subtract 10 from 2, the function's minus is applied to the arguments 10 and 3 to produce 7. And, you know, parentheses, parentheses, parentheses. Compound expressions like this get expressed in this way. So you add 2.1 to 4.3, and then multiply by 10, and then divide by that by 2. So in some sense, if you look at that, what goes first is on the inside, and then you sort of percolate out in terms of execution order. Okay. Of course, this is an unfettered language, so it has branching and looping and recursion and these sorts of things. Branching, it happens with an if statement. So if 4 is less than 5, which it is, then the return value of that expression is 1. Otherwise, it would be 2. So the return value of the if expression is 1. 1 added to 3 is 4. Okay, great. You all can read that, no problem. Yeah, it'll get complicated soon enough. In Cloture, Anglican, so on and so forth, functions are first class. So if you look at this, this is an anonymous function. This is kind of important, so let's read this carefully. So fn is a lambda, it's an anonymous function. It's a function of two arguments, x and y. And what it does is it multiplies its first argument x by 3 and then adds that to y. So if you apply that anonymous function to the arguments 10 and 2, then x gets bound to 10, y gets bound to 2, and 3 times 10 plus 2 is 32. Great. Okay, so that's an anonymous function, and you can pass functions around and name them. They're just like regular variables. You can use let blocks to establish local binding. So you can sort of rewrite that complicated function expression like the following: let x be 10, y be 2, and then the return value of this let expression is 3 times x plus y, as before. Okay. Everybody can read that, no problem. All right. Anglican and Clojure support higher order operations like map and reduce as well. So if we want to apply the function f of xy equals x plus 2y to the x values 1, 2, 3 and the y values 10, 9, 8, then we can map a function of two variables, 2 times y plus x, over the lists, actually vectors 1, 2, 3 and 10, 9, 8. And if you pairwise compute that, you'll see that it produces 21, 20, 19. And you can reduce as well, and everybody knows MapReduce probably better than I do. Reduce recursively applies a function to result in the next element, so on and so forth. So reduce plus 0 and a list does the following operation. It adds 0 to 1, takes that 1 and adds it to 2, and then adds that, so on and so forth, and that will evaluate to 10. Okay, great. So that's as much syntax as you need to know. So now you've learned Cloture and Anglican, almost, in 3 slides, right? So without further ado, that's boring. Let's get to the fun stuff. Let's do one example program. We'll do a number of programs just to see what Anglican programs look like, to give you a sense of what they're about, and then we'll talk about inference. So let's take the same bugs graphical model that we looked at before and look at what it looks like in Anglican. So here we have a thing called def query. This is really a model, a specification of a conditional distribution. And we're going to call this Gaussian model. It's a Gaussian unknown mean model, and it takes some parameter data. What does it do? It says let x be a sample from a normal distribution with mean 1 and standard deviation square root of 5. let sigma be a constant, which is just the square root of 2, and then let us map this function of a single argument y, which does the following operation: observe normal with mean x, standard deviation sigma, taking value y. We'll map that over the data, and then we're going to predict x. Okay? So this corresponds to the mathematical notation on the right-hand side. X is normally distributed, blah, blah, blah. Y given x is normally distributed like so. Let's say we have some data set. Here it's, let's say, 9 and 8, for instance. And what we're after is the conditional distribution of this model, characterized in some way. Here we're going to use particle Gibbs, and some number of particles is 1,000. Where the data set is plugged in, right? So we're going to say x, this posterior distribution is the posterior distribution of x conditioned on y, this data set. And what we'd like to see is that this thing is normally distributed with its analytically derivable mean of 7.25 and standard deviation or variance of 0.91. And what you see when you draw samples from this posterior distribution is, in fact, that is the case, okay? So, great. What do we have? So we have some language. It's a full-fledged, no holds barred language up here for specifying models with constraints. Okay, so we talked about randomness. So here we have, I should say, Anglican has first-class distributions as well. So we have distribution objects, we have the ability to sample from them, and we have the ability to introduce constraints via this observe function. Okay. And the semantics of the language are a little bit odd, but they should be relatively straightforward, which is to say that that model represents the conditional distribution of x given the data. Okay? Great. So running that program is tantamount to generating samples from the posterior distribution. Okay? To be a little bit pedantic, everything including the def query, but inside the def query is actually a different language, and that is Anglican. Now, we've designed Anglican in Jan Willem van der Mint and David Tolpin radically redesigned Anglican since the first paper on Anglican, and it made it basically syntactically indistinguishable from Cloture, which is a good thing. But bear it in mind that the stuff inside of def query is actually a different language. It has different semantics, has the same syntax as Cloture, so on and so forth. And that's often the case. Say, for instance, for web people, it's the same thing. There's a different language inside of the query, so on and so forth. So everything outside is Cloture, everything inside is Anglican. So I'm going to skip all of the outside stuff, even though that's how you actually use and compose distributions. But instead, what we're going to do is just look at how you specify distributions as constrained programs. And we'll do a couple of examples just to get you used to how it looks. So a classic example is a BayesNet, for instance, right? I'm sorry I didn't credit the person who actually drew that BayesNet. I stole it from somebody, so if you're here, I apologize. But here's a classic BayesNet. Let's see what this looks like. So we have, let's call this a sprinkler BayesNet. So we have cloudy as a sample from flip. Flip is just a coin flip. It's a weighted coin. Here it's uniform. So cloudy is going to be true or false. Raining is a sample from a distribution, which is either flip 0.8 or flip 0.2 if it's cloudy. If it's cloudy, it's flip 0.8, and you sample from that, and raining takes a value of true or false. Sprinkler dist is a distribution which is either flip 0.1 or flip 0.5 if it's cloudy. We observe that the sprinkler is true, so we set the value to true, and then we observe that from the sprinkler dist that sprinkler is true. Wet grass dist is a little bit more complicated, but that's just the encoding of the conditional probability table for wet grass, which is a conditional which takes ands and ors of the values of sprinkler and raining and produces a different kind of distribution. And we observe that wet grass is true. And then we ask to predict whether it's cloudy, raining, or whether or not the grass is wet. Of course, the grass is wet because we observed that it's true. But this program specifies the conditional distribution of cloudy and raining given that wet grass and sprinkler are true. Okay, easy examples. We've got a first hidden Markov model, now we've got a Bayes net. Great. How about a hidden Markov model? Okay, so this is one hidden Markov model. Okay, so def query HMM. Great. So this is one HMM. So the initial distribution is just a discrete uniform over 3, for instance. That could be any piece of code there you want, really. Transition distribution is a function which takes a state and conditionally returns a one of 3 different distributions. Discrete 0, 1, 1. So if you're in the 0th state, you can only transition to the first or second state. If you're in the first state, you can only transition to the second state, and if you're in the second state, you can only transition to the third state. You can only transition to the third state. In 0 versus 1 bounds. There's an observation distribution, which is a function of the state, and it's just a normal distribution with mean given by the state ID, the numeric ID. And we have 2 observations: y1 is 1, y2 is 2. X0 is a sample from the initial distribution. X1 is a sample from the transition distribution. Given the value of x0, x2 is a sample from the transition distribution given the value of x1, so on and so forth. We observe from the observation distribution, given the state at x1, y1, same for y2, and we ask to predict the posterior distribution of the 3 states that the HMM took. Great, okay? Just for the fun of it, obviously I made this a left to right HMM just because. This is, of course, not how we would actually write. So this is like data inlining. It's a gross way of doing this, and it's not how we would actually write this. If you have somebody like Jan Willem, I'll show a picture later. He's sitting up here, one of my postdocs. This is how you would write an HMM in Anglican. So this uses all the sort of glorious, gory functionality of the language. So def query HMM defines all hidden Markov models. So this takes as parameters y, so the initial distribution, the transition distributions, and the observation distributions. And then it predicts with a label x the following. So we reduce the function x, a function of 2 arguments, over, and you have to look down below to the square brackets that start sample initial distribution, over a sequence which starts by sampling from the initial distribution. That's the initialization of the reduction, and we reduce over the y's. And this function, what it does is it peaks it peaks in the list of x's. It gets from the transition distributions which have been passed in the distribution for that state, the transition distribution for that state, samples from it, takes that as the value x, then observes from the distribution that you get from the distributions that have been passed in, the value y, and then it adds that on to the state. And what this does is this reduction produces, by consuming every observation, a sequence of x's. And it predicts them with label x. Okay? So there's a generic HMM. And this now can be composed with lots of other kinds of things. So you can have different distributions for the initial distribution and transition distributions and compose them outside of Anglican. Okay. Note that if you pass in all of these parameters, there is no inference code. That's it. Maybe I should just make that very, very clear. That is the HMM. You don't have to write Viterbi or forward, backward, or bomb welch, or alpha beta message passing, or some product or whatever. That's it. You run that, you get the answer. Okay. Or the distribution over x's, as it were. Anglican supports unbounded recursion, and you might ask why this is important. We could spend lots and lots of time on it. So let's first look at the example and say, here's the geometric distribution. So def query geometric. So let dist be a coin flip distribution, and samp be, here's a new language construct, a loop construct, which is basically just a recursive construct. So loop in 0 binds the value of n to 0, and then executes the code block below, which is if, and you sample from the distribution. If that's true, then you return n. Otherwise, you recur by going back to the loop, but rebinding the value of n to +1. And what we do after this recursion bottoms out is we predict the value of the sample, which is just a geometrically distributed quantity. Okay, so this is about as simple as you can get and put it on the slide. It's an interesting point that if you have languages that don't support being able to write these kinds of distributions, you've automatically sort of tied your hands and made it more difficult, A, to extend the language, and B, to sort of innovate in terms of the kinds of models you would like to write down. Say, for instance, the church paper pointed out very elegantly that you need this kind of construct in order to represent, for instance, even the most fundamental Bayesian non-parametric object, the Dirichlet process and the Seth-Thurman stick-breaking construction. So if you think about what that's like, you break a unit interval recursively to infinity, and anytime you pick a label, you have to recur down some unknown depth. If you don't have this sort of ability or this sort of freedom in your language, then automatically all of Bayesian non-parametrics are out. You just can't do them. Right? So I put this here as an example of the kind of freedom that you need to have in order to write down any kind of model you would like, including Bayesian non-parametrics. But the Bayesian non-parametric stuff is really complicated to put on the slide. So last, let's look at the kind of model that that's a little bit more like the kinds of example applications that I pointed out before. So here we have a task. This is a programming exercise from the machine learning summer school this summer, where we would like to do some sort of constrained stochastic simulation. So here we have a query which we're going to ask to arrange some number of bumpers in between this ramp and this bucket over here, or box as it were. So we let bumper positions be empty for now, and we have this library function that we're going to call called create world, which takes the bumper positions, creates a world, and then there's a simulator. It happens that this simulator we just imported directly, so Clojure, Anglican, Clojure, Java, JVM. We can use everything on the JVM. So JBox2D is the physics simulator from Angry Birds. That is the simulate world. So we're just going to run a physics simulator here until the end of the world. We're going to collect the balls up and where they are, and then we're going to ask how many balls made it into the box. And we'll predict the conditional distribution of the balls, how many are in the box, and where the bumpers are in order to achieve a particular thing. And the goal here will be some world that puts 20% of the balls in the box. So what we can do is we can use our open universe, unrestricted, unfettered programming language to sample some number of bumpers here plus on 20, and to say put those bumpers anywhere we'd like. Say for instance uniformly in the x direction between 0 and 10 and -5 and 14 in the the other way around, y and x directions. And we sample some bumper positions, and then we run the simulation with those bumper positions, and we see what happens. Okay? So now we have a stochastic world and a deterministic simulator. So this is a lot like the vision problem or the capture problem or the constrained simulation problem, so on and so forth, where the positions of the bumpers are the graphical analogs of the latent variables in the problem, and obviously the number of them is Poisson distributed, so on and so forth. So if we introduce a constraint here, observing that there are 20 balls dropped, 4 of them on average make it into the end, then in fact the system will automatically infer a set of barriers that allow exactly that number of balls to make it in. So here we have, so what's the point? The point is, we can write anything over here on the left-hand side. It's a fully fledged modeling language. We can use any sort of library we want. We can use any sort of programming construct we want, so on and so forth. We can introduce constraints, and we can ask for the system to give us the posterior distribution over executions of the program that correspond to the constraints or satisfy the constraints. And it so happens that the same kind of inference, the same sort of inference techniques that we use here correspond to exactly the kind of inference techniques that correctly produce the posterior distribution for the HMM and for Bayes nets and for graphical models and so on and so forth. So the question is, what do those look like really? Okay. Now I did say that there is when you give yourself this freedom, you do open up the possibility of you open up many new ways of shooting yourself in the foot, really. So if you have this ability, you can write down models that really can't be inverted, right? So here's one of my favorite examples of a probabilistic program that you could write, but you ought not. So you might ask for the conditional distribution of strings that map to the same MD5 hash string. So here we have a length and an MD5 string that come in, so that's our observation and a length. So we sample from some string generative model, and then we observe that the MD5 of the string that we just sampled is exactly that of the MD5 string that we passed in, and we ask for the message. Okay, so this is captcha breaking, but it's not going to happen. It's cryptographic, right? So we can write programs now. So with this increased flexibility means that we've introduced additional burden on the programmer, but my personal belief is that that's okay. We can, when we're writing in C or any of these other unconstrained languages, we write programs that segfault and have memory leaks and so on and so forth all the time. There are lots and lots of different kinds of bugs. Here we're going to have a whole new kind of set of bugs where, for instance, you could write programs that can't be inverted, and that's troublesome, but one of the costs that comes with the flexibility. Okay. So hopefully by now, everybody sort of has a sense of what the goals of probabilistic programming are, where the systems have been, where we're going, what you get if you allow unfettered modeling languages, and in fact, maybe has a sense of how one might go about programming in, or what at least probabilistic programs look like in one of the languages, and sort of can maybe imagine how they would look in the others, given that it's basically a program with some constraints, and a query is just a posterior distribution of the variables given the constraints. The question is, how does inference in probabilistic programming languages, or these kind of universal probabilistic programming languages, work? Okay, and this is where we move on to how might you roll your own system, basically. Okay. So here's the gist. What we want to do is we want to explore as many traces as possible, basically, intelligently, where each trace contains all of the random choices made during the execution of the generative model. While we're computing that trace, we'll keep track of its goodness in some sort of way, probability as a side effect. And then we'll combine weighted traces probabilistically coherently and report some projection of the posterior traces. Okay, so that's what we're going to do. So what is a trace? In my mind, a trace is kind of like a many worlds interpretation of the program. So here's a little program down here in the bottom. Let T1 be 3, X1 be a sample from a discrete distribution where you repeat T1 times the value 1. And then if X1 is not equal to 1, then we do some other stuff. So let's run this program just for a second. So T1 is 3, that's great. So X1 is now going to be a sample from a discrete distribution where we, with 3 choices uniformly weighted. So X1 can take values 0, 1, or 2. So the first branching point of this program is this sample. So the program will run, and it will pick in any particular execution one value of x1, but in multiple executions may choose different values of x1 as you go. If x1 is not equal to 1, then the program continues, otherwise the program halts. We do some deterministic computation. T2 is x1 plus 7, and then we sample another value, x2, which is a sample from a Poisson distribution centered on T2. Okay? So now the first branching was finite because we had a discrete choice between three different choices. Here now we have a countable choice, and of course if this Poisson here were replaced by gamma or normal or something like that, we would have an uncountable branching of the execution paths of the program. Okay, so the goal is going to be to figure out how to basically either wiggle these traces or explore the space of traces in such a way that we compute a posterior distribution over there. Sorry, I have to blow my nose really badly. Thank you. Sorry. Back to it. So traces. Many world execution traces, we're going to explore traces by either wiggling them or exploring different paths sequentially. And what we're going to do is we're going to be able to take averages over the traces in a way that satisfies all of the, in a way that allows us to do statistical reasoning. Okay, so how do we, so I talked about what the goodness of a trace is. So here we have the same trace. So we have the trace evolving, but at the very end here we observe that x2 takes value 1 with very high probability. Okay, so we observe a Gaussian centered at x2 taking value 1, and that has with very small variance. So what does this do? It doesn't affect the trace, but it colors it in some way. It weights the trace in some sort of way, and it says actually, well, let's look at the top right here. The trace that goes through and takes value x2 equals 1, well, that's going to be a relatively high probability. It's going to be marked with relatively high probability. So the size of the circle here is how weighted the trace is. And correspondingly down below, the trace that has value x2 equals 1 also has higher relative weight to its neighbors. More importantly, perhaps, is that observation affects the entire weight of the trace, right? So because Poisson 7 gives higher mass to a 1 than Poisson 9 does, then that single observation tells us not just that the continuation of the trace from the rightmost point onwards is good, but in fact that the entire upper trace is more likely than the lower trace. Yeah? Okay. So let's be a little bit more formal. What's a trace? The trace is a sequence of in-observations, in-observed statements. So here, gi is going to be a distribution, phi I is going to be a parameter to the distribution, and yi is going to be the observed quantity. So these show up as the observed statements. And a sequence of m samples where f is a distribution, theta is a parameter to the distribution, and a sequence of m sampled values. So as you run the program forward and you encounter these sample statements, you're going to generate values x from those sample statements. And conditioned on these sample statements, the entire computation is deterministic. The trace probability, or a trace probability defined up to a normalization constant, is this gamma of x, which is the joint distribution of the sampled values and the observations with the value of the observations plugged in. That's the normalization constant. And we're just going to write this as the product of the observes, the g of i's, So this is going to be G of I, which is the probability of the y-ith observation given the parameter phi I, times the product of all of the sample statements. So the product of the value drawn xj given the distribution f and the parameter theta. This rather compact notation, and I would say that one of the things that the community, the probabilistic programming community, needs is actually some help with notation. It's very, very difficult to notate what's going on, but I'll try to at least show you why it's a little bit difficult to notate what's going on formally and super accurately. So whenever we write down a joint distribution like this, it hides the dependency structure implied by the program, or at least accessible by the program, which is to say that what's actually happening is that all of the distributions G, for instance, those I guess are the observed distributions, are functions of the random choices made up till that point in the program. So in other words, you can change the type even of the observation distribution. And the parameters to the observation distribution are functions phi I of the state of the program up until that observation. And same for the sample values. So in fact, theta j is potentially a function of all of the state that's accumulated at that point, and so too is the type of the distribution f. Great. So we try to notate this way with these sort of state space model-like notations, where x's are the sequence of samples, bold x's are the number of x's. So x4 is the set of x1 to x2, x3, x4. That's the samples, the four sample statements. yi is the first observed statement, so on and so forth. And the dependency structure is really everything chaining from the left. The program allows you to up to sort of syntactic access, variable access, allows you to write fully connected distributions with very, very complex dependency structure. But we're going to use the notation on the top and hope that you remember that in fact what's going on down is this bottom thing. And if you're going to help us with inference, you have to realize, even when you're reading our papers, which are not particularly clearly notated, that that's actually what we mean when we're talking about the dependency structure in our programs, induced by our programs. The inference goal is to produce a posterior over traces, which we'll call pi, which is just the posterior distribution of the trace given the observations, and we'll notate that thing, which is normalized, by its unnormalized brethren gamma, and the normalization constant, which is the evidence, which is just the integral of gamma over all possible traces. So that integral there is the integral over all possible execution paths of the program. And what we'd like to do is we'd like to produce samples such that we can compute Monte Carlo integrals, basically. So if we have some output from the program z, which is some deterministic function q of the state of the program, we'd like to be able to we use Q to mean question most of the time, or query, something like that. We'd like to be able to approximate the expectation of that function against the posterior as some weighted set of samples drawn somehow from the posterior distribution over traces. Okay, great. So let's quickly do 3 base algorithms and then see how we actually implement these things and make them run fast. So 3 algorithms for doing this are likelihood weighting, Metropolis Hastings, and sequential Monte Carlo. Likelihood weighting is pretty straightforward. It's not very efficient, but it's wicked fast. You run k independent copies of the program just simulating from the prior. So they just run the program, okay? So F here means just run the program. K is the instance of the program. MK is the number of random choices made in the kth run of the program. You might have a different number in different runs of the program. Our proposal is just to run the program forward from the prior, ignoring the observes. However, as you're running the program, we can accumulate unnormalized weights as we go along, i.e. whatever the system, whether we're running an interpreter or a compiled version of the program, we can run the program forward. And when we hit an observe statement, we can stop and say, hey, wait, we've hit an observe statement. We know what's observed. We know the parameter vector at that point, and we know the type of the distribution. So let's just compute a weight. Let's compute the likelihood score as we go along. So the weight of the unnormalized weight of a particular execution path of the program, wxk, is just the unnormalized joint over the unnormalized target over the proposal. And this proposal is going to show up later on. So when we do this, we run the program forward. We can use these in approximate Monte Carlo integration by renormalizing the weights and approximating the Monte Carlo integral by the normalized weights and our test function evaluated with each of the k independent traces. Okay, straightforward. Schematically, it looks something like this. You run the program forward. Blue is basically the deterministic part of the program running. You escape out to grab the likelihoods when you hit observe statements. You accumulate those in a weight. You compute the output of the program, whatever that happens to be, that predicts in our cases. And you do this k times. You get a set of k samples and weights, and there you go. Okay, so general purpose inference for probabilistic programming version 1. We know this isn't going to work particularly well because we're completely ignoring the data. Another way that one might think about exploring the space of traces is to use Metropolis Hastings. And so if we're going to do this, let's just remind ourselves that the posterior distribution of execution traces is proportional to the trace score with the observed values plugged in. Great, we already have that, gamma and pi from before. So let's use Metropolis Hastings. Let's make some sort of modification to the trace, move a trace around, and accept or reject a new trace and wiggle the traces like this. So if we use the standard Metropolis Hastings rule, where we have the joint of a proposed trace over the joint of our current trace, and the not necessarily symmetric proposal distribution Q for moving from one trace to the next, balancing out in the Hastings part of the Metropolis Hastings ratio, all we need is a proposal. So this approach to probabilistic programming inference first appeared in the Church paper in 2008, and subsequently in a paper called Lightweight Implementations of Probabilistic Programming Languages via Transformational Compilation, where they came up with a compiled version of this. So the lightweight Metropolis Hastings proposal looks something, or a lightweight Metropolis Hastings proposal looks something like this. If you would like to start at a particular trace XS and propose a transition to a new trace, then what you can do is you can go into the trace and pick out one of the MS samples in the trace and propose a local modification to it, change it with some sort of kernel kappa, and then continue the execution of the program onwards, running the program as you would, right? So with this proposal and quite a lot of bookkeeping, you can compute an acceptance ratio like so. So with a single site update, which means sampling from the prior, running the program forward. So we're going to choose a particular form for our proposal kappa, which is to basically just run the program forward from whatever the parameter was in the prior trace. Then the MH ratio simplifies to something that you can compute by tracking side effects as you run the program. So the acceptance ratio is the unnormalized joint of the proposal, the number of sample statements in the original trace, the probability of the original trace continuation restarting proposal trace at the nth sample, the number of sample statements in the new trace, and the probability of proposal trace continuation restarting in the trace at the nth sample. So we can compute all of these quantities by running the program over and over and over again, tracking when we make new choices. So this is a very quick summary of what's going on here. So what we do is we run the program once, we make all sorts of random choices and record all the random choices that we've made. Then we go in and we pick a variable here in the second line shown in red, and we say, okay, we're gonna change this. So provided that we've remembered all of the random choices that we've made in the first run of the program, we can run the program again using those values, and then run the program forward from the point where we make this proposal, tracking all the changes as we go. And say, for instance, when we compute the accept-reject ratio on this first pass, we reject the trace. That's fine. We just re-emit the first trace, and we continue on in a normal Metropolis Hastings sense, proposing variables to change, rerunning the whole program, trying to change that value, and then seeing what happens to the remainder of the trace after you make that change. Okay, that's the first two. Sequential Monte Carlo is also an option for general purpose probabilistic programming inference. So we're going to change notation just slightly, and we're going to notate the little blocks of the trace x twiddle 1 to x twiddle 2 as being the sets of variables in between or before every observation. And then we can write down the joint in an incrementalized form. So gamma of n is now the joint distribution of all the random choices and observes up to the nth observe. And we have an incrementalized target, which means that we can run SMC now. So if we want samples from the posterior distribution of traces up to n, we can note that it's proportional to the nth observation times the continuation of the program from the n-1th observation to the nth observation times the distribution over the posterior distribution over traces up to the n-1th observation. So we have a sample-based approximation to the quantity on the right-hand side, this posterior distribution over traces up to the n-1th observation, where we have the weighted sum of k different traces, where the delta function here is a delta function centered on a particular set of random choices made up to the n-1th observation. And pi n-1 is just this discrete distribution centered at all those atoms and weighted by w. Then we can sample from this distribution. So we can generate samples from the distribution of interest, pi n of x1 to 1 to n, by sampling from this discrete distribution by picking x1 to n-1, i.e. a prefix of the computation. The ancestor index there is picked according to the discrete distribution given by the weights. Once we've picked an ancestor, once we've picked a program run up to this point, then we can run the program forward by simply running the program as you would, and then concatenating the new choices onto the prefix of the program. And as we've then hit the next observe, we can compute an importance weight, which is equal to the observation probability of the nth observation given the trace up to that point. Okay, great. We renormalize the weights and go. This is standard sequential Monte Carlo. Schematically, I think it's a little bit simpler to think about. So in what we have is we run the program in parallel k times. When we hit an observe, we compute some sort of importance weight according to the observation that we encounter at that time. We resample and continue the execution of some subset of those programs, often and multiple times. So intuitively, we run the program, we wait and compute weights, and then continue. When you have sequential Monte Carlo, then variants like particle Markov chain Monte Carlo become available to you as well. So sequential Monte Carlo in the context of probabilistic programming is really just iterable sequential Monte Carlo, PMCMC, particle Markov chain Monte Carlo, is really, in the context of probabilistic programming, is really just iterable SMC. I'll give you one example of, of this PIMH, where if you run SMC, you can compute an estimate of the normalization constant using the weights that you compute along the way. And PIMH is a Metropolis-Hastings algorithm that accepts the entire new particle set with probability proportional to the ratio of the weight of the normalization constant estimate from one set of samples to the next. And you can rerun SMC over and over and over and over again, and all the particles and all of the runs of the program can be used. Okay, great. So that's the maths in a nutshell. Far too fast, but the basic idea is pretty simple. We have a trace probability. We want to run the program forward. The observations are the weights on the traces, and we can either wiggle the program by picking some value and seeing what happens if we change that value to the trace and computing a bunch of stuff that's Metropolis Hastings, or we can do SMC, where we run the program, we hit and observe, we wait, and then we basically fork the program and run the highest weight program, so on and so forth. We do this forward, and the particle Markov chain Monte Carlo methods basically iterate this SMC. So you can read all of that in the papers. There's a bunch of papers out there. Now, but the question is, how do we actually implement this? How do we make this actually run in a system? So the first thing we can do is we can build an interpreter. And this is the first generation of probabilistic programming systems that came out, particularly in this more expressive family, where we track the side effects and direct control flow for inference. The second generation, which is just coming into being now, is a set of compiled probabilistic programming systems, where because you aren't in control of the interpreter, you can only exert control over flow from within function calls, i.e. sample, observe, and predicts. But this, of course, this makes things a little bit more complicated, but it's lovely because it leverages existing infrastructure. Okay, and makes things fast. So let's think about one way to compile, or one kind of probabilistic programming language and one implementation strategy for a probabilistic programming language, probabilistic C. So this is one of the languages we worked on. You can run SMC in this, you can run particle Gibbs in this, you can run all of the PMCMC inference methods. So probabilistic C is standard C plus two new directives, observe and predict. Okay? So observe constrains program execution exactly as before, predict emits sampled values, it's C. Everything that C can do, it's C. So here we have an example of a probabilistic C program, you include probabilistic.h, you write a main file, and you run a program. This is the same Gaussian unknown mean example as before. We have some variance, a mean parameter mu, which is normally distributed, and we observe 9 and 8 coming from a normal distribution with mean parameter mu and variance, and we predict mu. Okay, so probabilistic C is compiled using a standard compiler, standard GCC compiler, and it performs the same kind of inference as before. And how we do it looks like so. The probabilistic C implementation does this. It actually runs the program. So it's kind of fun. The implementation is macro rewrite main and run it in parallel multiple times. When you hit an observe, you wait for everything else to get to the observe, and then you compute the importance weights in some sort of shared memory space, and literally you fork. Okay, it's kind of fun, right? So some processes die, other processes continue in multiplicity, right? So now we have no control over the execution except that we own the implementation for observe, which means that when the program hits observe, we can stop its execution, wait for all other executions to stop, and then we can force the program to continue once or multiple times or stop. Okay, so the rest of a program in a C context is just keep going, return from the function, or fork. Fork gives you the ability to explore multiple downstream paths, right? So you can take a process and fork it, and it will run multiple continuations independently and in a way that doesn't cause any sort of interference on the prefix of the computation, i.e. in the trace variables that have been established up to that point. So it's sort of a complicated way of getting around to the point that what we want in order to do inference efficiently, compiled inference in these programs, is access to continuations. So certain languages give you explicit control over continuations, many do not. But a continuation is a function that encapsulates the rest of the computation. There is a programming languages trick called a continuation passing style transformation, which rewrites programs such that no function ever returns. Every function takes an extra argument, a function called continuation. It's a standard programming languages technique. You can look it up in a book. And it's been used in probabilistic programming systems and is now the basis of for instance, WebPeople and Anglican. So what does a CPS transform look like? Well, first we take regular closure here like so. Let's look at this for just a second. Print line plus add 4 to 2 times 3. If we CPS transform this, we're going to need a couple of, okay, what's happening here? So times ampersand is a new CPS transformed function, which is down here on the bottom, which is the original function times, and also takes a continuation, and then calls the continuation with the result. Plus is the same thing. It's the original function plus, takes the 2 arguments a, b, and then calls the continuation with the result. So when we transform the standard closure up above into the CPS transformed version, it works out like so. So the innermost operation times 2, 3 becomes the first operation. So we pass 2, 3 to times ampersand. And the function x, which is then the first continuation, which is what to do after you multiply 2 times 3. And that function takes x and calls our CPS transformed version of plus, which adds the value of 4 to 2 times 3, and then calls print line with the result. Okay, this is a standard kind of technique. CPS explicitly linearizes execution. So if we're going to do something complicated like compute the square root of x squared plus y squared, we can CPS transform such an operation as well. So we square x and we call the continuation with the value, and we square y and we call the continuation of the value, and then we add those, we call the continuation, we take the square root, call the continuation, so on and so forth. Okay? Don't have to get all of that. It's very, very fast. Anglican, let's look at the example here on the upper left-hand side. So here we have a beta binomial example. So flip example with given outcome says, let P be a sample from a uniform continuous distribution on 0, 1. We observe a flip of that coin taking a particular outcome, and we want to predict the weight on the coin. So we have the Anglican program on the left-hand side, and we have sort of a linearized version on the right-hand side, which uses a let block to sort of name all the random variables. So Anglican is actually compiled now to native continuations passing style closure. So if I flip back and forth, so that query is actually just an Anglican, it turns into, effectively, just a closure function, which takes a particular outcome and a continuation, and first calls uniform continuous, then calls the continuation function with the output of that function, whose implementation is given here, uniform continuous ampersand is the CPS distribution constructor, which constructs a distribution and calls a continuation with that distribution. So uniform continuous constructs a distribution, calls the continuation with that. That function, fn dist1, calls sample with that distribution and takes the result and calls another function with that result as its argument p, and that constructs a function and then calls it so on and so forth. That function calls flip and observe and so on and so forth. So we have a linearization of the program, but the critical part, and this is really the only take home that you really have to get from this, is that by doing this transformation, we have made explicit the rest of the computation. Yeah? So all of these functions here pointed at by the blue thing are what to do after you do these, the uniform continuous. What do you do next? Sample. What do you do next? Flip. What do you do next? Observe. What do you do next? So now we have a linearization of the program. Great. We have all of the Anglican primitives, and these show up as closure functions as well. And what we have now is the beginnings of an inference backend interface where sample, observe, and predict are functions that we provide, and we can override to perform different styles of inference within a fully compiled environment. Okay, so that's that. So this common framework looks like this. So we have a pure deterministic computation. It's we've done this CPS transformation. We've got Anglican transformed to CPS style closure, which then itself is just in time compiled to the JVM by the closure compiler. So everything is compiled all the way down, super fast. We control the functions sample, observe, predict, and terminate, and we control the outer loop. And we can call our function, and it's going to start the computation. And when that computation hits a sample statement, it's going to pass to us a distribution, its parameters, and a continuation. We can do whatever we want to with that distribution, the parameters, and then call the continuation and resume the computation at that point. Same thing with observe. So observe will pass us the observation distribution, its parameters, the observation value, and a continuation to call, and we have that continuation. We can call it and go forward. Predict will give us the deterministic output that's produced by the program Z, and a continuation call, a continuation, and terminate, so on and so forth. So it's a very long-winded way of getting around to saying that basically, if you take this approach of compiling your programs into this representation, the CPS representation, then your backends become basically an outer loop and an implementation of three functions. Sample, which takes a distribution and embedded within it the parameters to that distribution, and a continuation, does something specific to the algorithm, and then calls the continuation with a sample from the distribution. Observe gets a distribution and the parameters inside of that, the value that was observed from that distribution, and a continuation to call. You can do whatever you want. You can print out a log weight if you want to, but now we have some sort of algorithmic specific implementation here, and you continue on. And predict similarly. You get a label, the value, and a continuation, and you just call the continuation. So for instance, what does sequential Monte Carlo look like in this? So we have some sort of outer loop, which I don't show here, where you run the program in parallel k times. Every time you hit a sample, that is the SMC backend code. You call the continuation, sampling from the distribution. Great, sample from the distribution, call the continuation. The code for observe is a little bit too long to stick on a slide, but it blocks and waits, as you would expect, for k calls to reach the observe. It computes weights. It uses the weights to subselect continuations to call, and then it calls continuations k multiple times. So you have access to the remainder of the computation, it's all compiled, and you're going to call those continuations multiple times, and this is how you're going to get SMC to explore different branches depending on the weights that you compute. And predict is as shown. So when you do this, nice things happen. So we have this unrestricted programming language, Anglican. We do this programming language technique, transform it into some sort of linearized form where we have control over continuations. We have explicit control over continuations. What happens is that basically a very large number of inference algorithms that can be used for general purpose universal probabilistic programming inference can be implemented and deployed in this very fast compiled inference backend framework. So for instance, in Anglican, we have 14 different inference algorithms already, 14 or more. And basically, every one of those inference algorithms is about 165 lines of code. So if you're working on inference and you want to try out implementing an inference algorithm in a system, this is maybe not such a bad way to go. So so we've got sequential Monte Carlo, likelihood weighting, particle cascade, particle Gibbs, particle independent metropolis Hastings, particle Gibbs with ancestral sampling, lightweight metropolis Hastings, adaptive variance of them, Bayesian descent Monte Carlo, map estimation via simulated annealing. And all of these kinds of inference techniques can fit inside of this framework, which is a compiled framework for doing inference in general purpose universal probabilistic programming languages. Great. So, where do we stand? The probabilistic programming concept is pretty well established. The community, although it hasn't necessarily been named as a community, has been around for a long time. There are lots of different languages. Different languages have different restrictions. Different restrictions lead to different inference algorithms. If you do the universal inference, if you do the universal probabilistic programming language, you have all of the complications of dealing with a real programming language. There are inference techniques that work for model specification languages that are fully featured and general like that. And in fact, we can even perform inference in a compiled environment, so we can actually go fast. Great. So it's well established. We know what's going on. The tool maturity is rapidly increasing. So for the youngsters out there who are doing homework on generative modeling or so on and so forth, I would go look at Venture and try out a Venture interactive shell. Try WebPeople, try WebChurch, so on and so forth. You can probably do most of your homework actually in such a system now if you're going to do general purpose generative modeling kinds of stuff. For prototyping models, we use systems all the time now. So if you're going to try out a new model and see how it works, or you want to try writing down a model that you can't quite figure out how to do inference in, this is we're ready for that. Research, definitely. We're writing new models all the time now that are difficult to think about writing down in any sort of way, very much akin to the kind of example applications that I put out early in the talk. And some of those models are pretty interesting. I would say that we are actually at the point, thanks to the sort of advanced inference methods, or advanced compiled inference methods, we're at the point where we can actually handle small real-world applications, and you should really actually consider using probabilistic programming systems to help you achieve your aims. However, there are some gotchas and there's some real stumbling blocks, which is to say that there are some highly optimized models that you know and love that don't necessarily scale all that well in current probabilistic programming systems. If you're going to do LDA, I wouldn't do it in a probabilistic programming system. If you're going to do neural nets, I wouldn't do it in a probabilistic programming system, at least not yet. There are some interesting opportunities to for future research, not least of which include writing models in these languages and in developing new inference algorithms, so on and so forth. On the programming languages side, there's a bunch of people who are trying to automate what sort of best practices from machine learning by working on program transformations that simplify or eliminate inference entirely by moving observes up and out. So there's some work by Ken Shan's group in Indiana where you take, say for instance, this Beta Bernoulli program on the left-hand side and figure out semantics preserving transformations of the source code that allow you to take the observe statement and move it all the way out of the program, meaning that there is actually no inference left to be done. So you have a beta, a sample from the beta, a flip with that parameter, and we observe an observation with that likelihood. It's very clear that there's a conjugacy that can be exploited here. So if we if we do that, we should be able to actually just add the count to the observation, to the parameters of the beta, as I do on the right-hand side. And in fact, there are systems that do these kinds of transformations now, and more they're able to sort of exploit all the conjugacies and even identify some algorithmic opportunities for eliminating inference. I think the most exciting thing, and I wish that I had a lot more time, is the development of data-driven and adaptive proposals for the kinds of general-purpose inference engines that are required in the kinds of probabilistic programming languages that I've talked about. So there's just a little shout out for a workshop that will be happening later this week, the Black Box Learning and Inference Workshop, where we'll talk about this a fair amount. I didn't mention this earlier, I started to just a bit. In the picture example, the picture probabilistic programming language for scene perception, one of the ways that they were able to actually get that to work is to use, amongst other things, neural networks that map from, in their case, only the observation space, but in the general case, the observation space and the environment of the program as it's running, to suggestions about how the program should proceed forward from there. And if I can talk and you're willing to engage with me, I would love to spend a whole bunch of time talking about this, because I think this is actually really the most exciting area for probabilistic programming, and frankly, actually neural nets as well, where we can sort of think about probabilistic programs as ways to train neural nets to do things that are interpretable, and we can think about neural nets as ways to compute very powerful proposals for general purpose inference engines in order to make inference much easier than it is and make it tractable to actually solve all kinds of problems, any kind of problem that you would write down in one of these universal probabilistic programming languages. So to conclude, if you work on inference and you do it inside of a probabilistic programming system, then any inference algorithm you come up with, by virtue of it being hidden behind this programming language abstraction barrier, will apply to any of the models written in that barrier. And as those models get more and more expressive and make use of the facilities of having a general purpose language and simulation environment, those models will begin to approach the kinds of complexities and expressivities required to solve the most interesting problems facing us. So working on inference or working on probabilistic programming system, working on language, so on and so forth, this all is going to bubble up and move the field forward quickly. I have some go-to resources that I think I should put in front of you so that you're aware of them if you aren't. There's a fantastic resource out there for writing your own probabilistic programming language. It's dipl.org. This is the Stanford people who put this out there. My favorite model repository, short of the Anglican one, is forestdb.org, where there's a whole slew of very interesting probabilistic programs out there that stretch your imagination and make you think about what's doable with a probabilistic programming system. The easiest places to start, given that they're browser-based languages, are webpeople.org and probmons.org. And the place to find all of the probabilistic programming literature in one place, although now that Dan has moved to Toronto, it's not maintained quite as often as it used to be, is probabilisticprogramming.org, which has a list of all of the papers and systems. And I'd just like to throw out that if you want to go someplace to look at sort of where the field is going, sort of some of the most advanced ideas in probabilistic programming, then you're well. You should go check out Venture at that link. If you're interested in engaging with Anglican at all, there's a bunch of Anglican resources out there. There's the Anglican website, which has a bunch of help and general information. If you want to learn probabilistic programming through Anglican and with Anglican, there's a tutorial that we put together for the Machine Learning Summer School this year, which is available there, which takes you through in about an hour, getting up to speed programming in Anglican. If you write applications, you want to use it for your own particular use, there's a pre-configured applications environment. You pull that from that repo, and you'll be ready to go in minutes. If you'd like to look at the core or look at inference algorithms, Anglican is open source GPL v3. You can download it from that link. And if you want to get started with existing applications, there's a repository of examples that you can also pull and install and play with. So, some final thoughts. Adopting the kinds of abstraction boundaries that suggested by probabilistic programming practice will, I think, actually move the field of machine learning forward much faster by making it easier for inference and modeling experts to work together. So I would encourage all of us, and I'm so frustrated that I feel as sickly as I do, because I'm not exhibiting the kind of excitement that I actually feel about this. I think there's real power to thinking in this way, and to using the tools of programming languages and abstraction to really accelerate progress in the field. And just to make this point, because it's easy to lose sight of this, probabilistic programming is not about magically making inference easier, right? We haven't changed inference. Inference is still hard. It still has the same formal hardness as before. But instead, it's about making it possible to denote and work with generic, richly expressive models that would be unimaginably difficult to work with in any other way. And we're going to see in the next few years some very, very interesting models that come out that are expressed in this way. So I owe a great deal of thanks to Jan Willem Vendement and Brooks Page, who are here. Jan Willem is on the faculty market, and Brooks is graduating and is either looking for a postdoc or maybe a faculty position as well. David Tolpin is responsible for our transition from interpreted to compilation. And he's already gone. He's gone to PayPal Research in Israel, so you're a little bit late for him. There's some other folks in my lab who have helped out on the probabilistic programming side quite a lot. Yura, Tuanan, and Hongsuk Yang, a collaborator in computer science. And I owe a great debt to Josh Tenenbaum and Vikash Mansinga, who hosted me in their laboratory and got me started on probabilistic programming several years ago. And I have to gratefully acknowledge DARPA for funding not only my lab, but a great deal of the work in modern probabilistic programming. And I'll leave this up, and thank you for your attention. Thank you for your time. Sorry for all the coughing and illness, but hopefully you got something out of this, and I look forward to interacting with you throughout the remainder of NIPS. Thank you very much.